Welcome to Lesson 13b, Prandtl-Meyer expansion fan integral. In this lesson, we'll analyze the differential change of Mach number and flow angle across a single expansion wave, and then I'll show you how to integrate that to get the general Prandtl-Meyer expansion fan integral. First, a review. We're talking about flow over a sudden change in the wall angle, angle delta, where we get an expansion fan. This is the figure from the previous lesson where I show all these angles. Here we're interested in one of these expansion waves. Take the very first one, the leading wave for example, and let's magnify here what's happening across this wave. We have an infinitesimal change in the flow angle, which I'll call d theta. Mach number also increases infinitesimally, as does v. Notice that the speed downstream of the expansion wave is both larger than v upstream and is tilted at some angle d theta. We split v into tangential and normal components, and we do the same for v plus dv. The key, which is the same as what we did with oblique shocks, is that vt, the tangential component, is the same upstream and downstream of this expansion wave. In other words, this tangential component is not affected by this expansion wave. Let's analyze some of these angles. Both of these are right triangles. So this angle is pi over 2 minus mu, since the angle on the opposite side is mu. And similarly, since this angle is mu plus d theta, and looking at this larger triangle here, this angle is pi over 2 minus angle mu plus d theta, or pi over 2 minus mu minus d theta. Now hold on to your hats, because we're going to do a lot of trig, with the goal of finding an expression for d theta in terms of speed v and dv, so that we can then integrate over the whole expansion fan. Keep in mind that this is just one wave of the expansion fan. You may remember these equations for sine alpha minus beta and cosine alpha plus beta, and this is an infinite series for 1 over 1 minus x. From this right triangle on the left, we see that vt over v is equal to the sine of pi over 2 minus mu. I'll call that equation 1. If we do a similar thing with this triangle on the right, we have vt over v plus dv equals sine of this angle, pi over 2 minus mu minus d theta. I'll call that equation 2. Now let's equate vt in equations 1 and 2. We have v sine pi over 2 minus mu equal v plus dv sine pi over 2 minus mu minus d theta. A little bit of algebra gives us 1 plus dv over v equals sine pi over 2 minus mu over sine pi over 2 minus mu minus d theta. I'll call this equation 3. Now let's use our trig identity on both the numerator and denominator in this equation. For the numerator, we get sine pi over 2 cosine negative mu minus cosine pi over 2 sine negative mu. But cosine pi over 2 is 0, and sine pi over 2 is 1. We also know from simple trig, if this angle is mu, that cosine of mu is the same as cosine of negative mu. So this becomes cosine mu. So the numerator of 3 is just cosine mu. Now consider the denominator. First, let's generalize. Since we just showed that sine pi over 2 minus mu is cosine mu, we can say that in general, sine pi over 2 minus any angle theta is equal to cosine of that angle theta. Thus the denominator of equation 3 is sine of pi over 2 minus mu plus d theta, which if we let this be theta, we get cosine mu plus d theta. Now let's use the other trig identity for this term, giving us cosine mu cosine d theta minus sine mu sine d theta. This is the denominator of equation 3. Thus equation 3 becomes 1 plus dv over v equal cosine mu over cosine mu cosine d theta minus sine mu sine d theta. I'll label that equation 4. But since we're talking about differentials here, d theta is very small, and we know that sine of d theta is approximately d theta itself when theta is small, and cosine d theta is approximately 1. So 4 becomes 1 plus dv over v is approximately cosine mu over cosine mu times 1 minus d theta from here sine mu. And in the limit as d theta goes to 0, we can change this approximate to equal. Now let's divide top and bottom by cosine mu. We get 1 plus dv over v equal 1 over 1 minus d theta sine mu over cosine mu. But any good engineer recognizes this as the tangent of mu. So we have 1 minus d theta tangent mu. I'll rewrite that here and call this equation 5. Now use our series expansion. Equation 5 then becomes 1 plus dv over v equal 1 plus d theta tangent of mu plus higher order terms, which we can neglect as d theta or dv get infinitesimally small. The ones cancel here, and thus d theta becomes dv over v divided by tangent mu, which I'll call equation 6. I'll do one other trick here. We know that for a Mach wave, Mach angle mu is the arcsine of 1 over Mach number. But if I sketch a right triangle with angle mu and let the hypotenuse be m and this short side be 1, we know that this long side then is square root of m squared minus 1. This comes from the famous Pythagorean theorem, as Scarecrow of the Wizard of Oz demonstrated.
Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, John, lecture! I've got a brain!
And I hope you picked up that Scarecrow actually said it incorrectly. Well, we see from this triangle that tangent mu is 1, this side, divided by square root of m squared minus 1, this side. And let's plug this into here so that equation 6 becomes d theta equal square root of Mach number squared minus 1 dv over v, which I'll call equation 7.
Hey Doc, I didn't see that you used the ideal gas approximation anywhere in this analysis.
Great observation, Arnold. Equation 7 holds for any 2D supersonic flow, even for a non-ideal gas. As Arnold pointed out, we never used the ideal gas approximation in this derivation. Finally, we need to integrate equation 7 across the whole expansion fan. I'll re-sketch the expansion fan at a sharp corner from 1 to 2 with M1 and M2, where let's call this angle theta 2 and let theta 1 equal 0, since the flow at 1 is horizontal. So we can integrate equation 7 from 1 to 2 across the expansion fan, giving us the integral from theta 1 to theta 2 d theta equal the integral from m1 to m2 of the square root of m squared minus 1 dv over v. The left-hand side integral is trivial, theta 2 minus theta 1, but we're going to have to work on this right-hand side. We'll have to write v and dv in terms of Mach number so that we can integrate. But for now, we'll leave this as equation 8, and we'll call it the Prandtl-Meyer expansion fan integral, which, as we've pointed out already, is valid for any gas, not necessarily an ideal gas. In the next lesson, we'll integrate this for an ideal gas.
Hasta la vista.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.
That's all there is to it.